Okay, so now today we are going over concept 3-9, free fall motion. So we have about 4 questions to go through, so let's get started. So we're going to start with 3-9, question 1. This question is asking about weight. If you recall, weight, the force of weight, is equal to the mass of an object times its gravitational acceleration, and we know that gravitational acceleration, as long as you are on the planet Earth, is equal to 9.8 meters per second squared. So let's go through the question. An object sitting on a table, has a weight, and its acceleration is equal to 0. So let's draw this out real quick. So there's some object, it's just a box, it's a happy box because it likes learning physics. It's sitting on a table. So is there any motion associated with this? I'm just sitting there, you know? So from this piece of information alone, sitting still on a table, we can assume that no motion is occurring. So if there's no motion, there's no acceleration. So acceleration equals 0. So option A says the object has a weight and its acceleration is equal to 0. Well, we just went through and said that acceleration is equal to 0. So the options that say it's not equal to 0 are false already. So B and D are out, because what these are saying is even though it's sitting still on the table, it's breaking through that table because it's like suddenly it's at this table here and it just like broke through it because it was able to overcome the force that was pushing it up against it. Because if it's sitting still, it has equal forces in opposite directions. So the contact force, it would be equal to the weight if acceleration was equal to 0, which it is because it's sitting still. But if it was equal to 9.8, well, there is no opposing force. It's just breaking through that table, which is kind of crazy. I mean, I don't know how heavy that box would have to be to break through that table, but it's pretty wild. So from that information already, we know that any answer that says acceleration is equal to 9.8 meters per second squared is false. And then the final thing we have to discern is whether the object has a weight or not. So as we discussed in our last video, as long as something is on the planet Earth and it has a mass, it will have a weight because it will be subject to the gravitational acceleration of Earth. It is being pulled by Earth as long as it has a mass. So something like a box sitting on a table has a weight force associated with it. So C says it does not have a weight, but that is false because it has a mass and therefore has a weight. So A is the correct answer. Okay, so moving along here, we have 3-9, question 2. And this is a definitional question asking us the definition of free fall. So an object is in free fall when free fall is just when the only force acting on the object is the gravitational force of an object. So it would be the weight force, basically, but it's like in the air. So this only occurs when an object is only being acted upon by the gravitational force of Earth. So this occurs let's imagine you have a baseball. You just threw a baseball up in the air. As long as it was in your hand, it was experiencing. So let's erase this real quick. I want to draw it in your hand versus not in your hand. So when it's in your hand and you're revving it up to throw it up, like it's still in your hand, but your hand is going upward. If we drew a free body diagram of that ball, the force of your hand is going upward, and the weight force is going downward. So this would not be free fall. This would be the initial amount of energy, the initial amount of force that you placed on that ball. But let's erase this ball and put it above the hand now. Once it leaves your hand, there's that space, there's that gap between your hands now, you could see. The only force acting on it is the weight force. So you gave it force pushing it upward. It's going to continue going upward, but it's going to be accelerating downward the whole time. So it's in free fall from the moment it leaves your hand to the moment it hits the ground again. So this whole time going upward, it has free fall. When it's at its apex, it has free fall, and it has an acceleration of negative 9.8 meters per second squared. And as it's coming down, it has a free fall. So going through these answers, answer A says only when it's moving vertically downward. Well, no. When the object is moving upward, it is still experiencing free fall because it's only experiencing the weight force associated with it. It is always experiencing the force of gravity on it, but it's still moving upward. So therefore, A is false. Part B, anytime it feels the force of gravity. This is false as well, because if it's sitting on a table, if this baseball was sitting on a table, very big baseball, may I add, if we were to draw the free body diagram, it's still feeling the force of gravity, but it's also feeling the contact force. And we're going to say these are equal. So therefore, B is false as well. Only if the weight force is the only force acting upon it. We'll get back to this one in a second. We know this one's the correct answer, as I've been explaining. But let's just go to explain why part D is false. Anytime an acceleration is equal to 9.8 meters per second squared. So this is false because a ball could be moving, like let's say down a slope, moving down a slope. It could have an acceleration of 9.8 meters per second squared, but that doesn't mean it's in free fall. There's still an opposing force, an opposing normal force acting upon that ball as it's rolling down at 9.8 meters per second squared. So therefore, this is not the case, as free fall is only defined as when the weight force is the only force acting upon the object. On to question 3. We see that you throw a ball straight up into the air. The ball experiences free fall motion. At the highest point, the balls... So let's just map this out real quick. We're going to draw two graphs. Position versus time graph, and then a velocity versus time graph, because that gives us all the information we need to answer this question. So this is our position versus our time graph. This is time. And let's assume we're starting at position 0. This is equal to 0. And then we don't care what the top is, but at half the time it's in the air. So we throw a ball straight up in the air. And then this is when it reaches its peak. And then it comes back down, and hits the ground. This is position 0 again. So this is the end of when it's in the air. So if you recall, the slope of a position versus time graph is the velocity of the object. So when the slope is when the slope doesn't change, so we're going to do this in purple. If the slope were something like this purple line here, the slope is always the same. So velocity would be constant throughout. If we were to plot this on a velocity, if this purple line on a velocity versus time graph, the velocity would be constant throughout. But for this problem here, we see that velocity is changing throughout. I'm going to draw this in. I'm going to erase the purple lines and draw this in red. If we look at the slope over time of the position versus time graph, we see that at time 1 has this really steep slope, time 2 kind of less steep slope, continues to decrease, and then at that point it's at its apex, it has a velocity of 0. Then the velocity becomes more negative, until it reaches the floor. So let's now plot a velocity versus time graph of each of these slopes. Because if you recall, the slope of a position versus time graph is the velocity of the object. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points to plot. So in red here, we have this velocity versus time graph. And we know that direction matters when it comes to velocity. So we start off positive, and then we see that the slope decreases. So as time passes, the slope is decreasing. It continues to decrease, and then when it reaches its apex, that slope is flat. So it has a slope of 0. It has a velocity of 0. And then we see now the slope is negative. So it's becoming more negative, until it hits the ground. And as we can see here, this velocity versus time graph has a negative slope. And if you recall, the slope of a velocity versus time graph is the acceleration of the object. So as you can see, if you were to plot the slope, which is acceleration versus time, let's do one last graph here, just for the purposes of explanation. If we had acceleration versus time on this purple graph, we see that the slope is always, it's constant and it's negative. So it'd be some value here. It's not on the it's not at 0, and since we're on Earth, we can just assume it'd be like negative 9.8 meters per second squared. But as you can see, that slope is always constant. There's no point at which velocity, the slope of this velocity curve, flat lines. If it were flatlined, acceleration would be equal to 0. So therefore, the acceleration is always constant, and it's negative 9.8 meters per second squared in this case. So with these pieces of information, we can now finally approach this problem. So I'm going to come back to the color blue, and we're just going to go through the answers. So at its highest point, so this point right here, is the velocity and acceleration equal to 0? Well, we see here that this point here transposes into this point here. And so velocity is 0, but acceleration, as we just said, since the slope of this is always negative 9.8, acceleration is not equal to 0. It's equal to negative 9.8 meters per second squared. So therefore, A is false. Part B says velocity is non-zero, but acceleration is 0. Well, that's false too. Velocity is 0, and acceleration is non-zero. So this one is the most incorrect answer. So we're going to give this one this one is trying to trick us. So I'm giving it a really frowny face. Part C says acceleration is non-zero, but velocity is 0. That is correct. Velocity at the point of highest position has a velocity equal to 0, because as we said, this is 0. And its acceleration, if we were to transpose that point, is right there. As you can see, that is a non-zero acceleration. So therefore, C is the answer. And just for the purposes of analyzing the question, let's look at part D. Velocity and acceleration are both non-zero. Well, we already said that velocity is 0, because when we transpose the change in the slopes over time, we see that at the highest point, the slope transposed to 0 velocity. So therefore, C is our correct answer. So our final question here is similar in nature. It's just testing a very similar concept in just a slightly different way. Instead of trying to map out the question yourself, it's asking you to analyze graphs. So this one is a graph analysis question. So graph analysis. So let's just get through this. You throw ball 1 up straight in the air at the same instant that you let go of ball 2, so over the side of a balcony. Which velocity versus time graph best represents the motion of these two balls? We assume air resistance is negligible, so there's no like funny business going on. It's only the force of Earth that's acting upon these balls the whole time. So let's draw out what's happening on this balcony. So we have this balcony here. We have you're this guy right here. And maybe just for the purpose of this, you're this beautiful guy, have luscious locks, okay? And ball 1, you throw up in the air, and then, as we recall, the moment that ball leaves your hand, the only force acting on it is its weight force. And so even if it has an initially positive velocity, it always has a negative acceleration. So it reaches its apex, and as we said in the last problem, the apex is when velocity is equal to 0. So right at this point here, velocity equals 0. And then it falls until it hits the floor. But ball 2, on the other hand, we're going to draw this in purple. Ball 2, it starts from the balcony and is dropped. And then it hits the floor. So since it's dropped from this point, there's no initial velocity upward, and there's no initial velocity downward either. So at time 0, t equals 0, velocity equals 0 for ball 2. For ball 1, at time 0, velocity is greater than 0, because we had said that above you is a positive direction and below you is a negative direction. So with that context in mind, let's start analyzing this question, or these answers. So part B says that the velocity is positive for ball A and the velocity is negative for ball B, but they're being acted upon differently. So part B, or answer B, is saying that ball 1 is accelerating upward. It is going to the moon, but ball B is actually, or ball 2 is actually being acted on by the forces of the Earth, and it's coming down to Earth, while ball A is going to the moon. That doesn't really make sense, because if they're both on planet Earth, they should both be experiencing the gravitational forces of Earth and should have the same acceleration as a result. So B is false. C, we know that acceleration is constant throughout this whole process because we're still on planet Earth throughout the whole time the balls are experiencing free fall. So automatically, just by looking at this graph, you see curved lines and you don't see a straight slope, a non-zero straight slope. You know that C will be false simply because if we look at it, velocity for ball 1, velocity isn't increasing over time. Since the weight force is the only force acting upon it and it's acting in the negative direction, it should always only be increasing from time point 0. So that's one indicator that it's wrong. The other indicator is that the slope is changing over time. So for this velocity versus time graph, it should be a constant non-zero slope. So therefore, that's another reason why it's wrong. And then we don't even need to look at number 2 because that's a similar case, except it's just transposed down to velocity equals 0 to start. So this one's false as well. And then answer D says that ball 1 has an initial negative velocity, while ball 2 has an initial 0 velocity. So ball 2 here is correct because at time 0, there's no velocity, there's no acceleration occurring. There was no force added to this ball to give it an initial velocity. So therefore, at time 0, the velocity equals 0. So that's represented on this graph. But for the other ball, we had said that it's moving in the positive direction at time 0, and it's given an initial velocity because you threw that ball up in the air. So it should not start with a negative velocity. This graph right here with ball 1 would be saying that you threw the ball down with some force. Like you were looking over the ledge and you threw that ball over that ledge to hit the ground. So it essentially get a head start over ball 2. So that's why D is false, because we know that the velocity of ball 1 at time 0 is positive, not negative. And that leaves answer A, which represents all the information we gathered from the prompt. Velocity of ball 1 is positive at time 0. At some point when it reaches its maximum velocity, it crosses the x-axis, and then it starts to have a negative velocity and starts to travel downward. And then ball 2, it starts with a 0 velocity and decreases. And the last piece of information that's important to note is that these have the same slopes, which means they're being acted upon equally by the gravitational force of Earth, which means they have the same acceleration, which is true for any object that is on the planet Earth. So that's the last question we have here. Hope these made sense to you. If not, please let me know in the comments. I'll try to clarify any way I can, and have a great day.